All right, y'all, welcome back. Lots of logistics to talk about today. Lots of interesting things, good things. I don't know, not bad things. Nothing bad. Good or neutral, depending on your perspective. So, here we are, y'all. Here in the syllabus, I have my timeline at the end. We have 5 weeks left. 5 weeks left of heartwarming time together before we must go our separate ways. 3 weeks of content left. So we have today's week, we have this week, which is going to be Faraday's Law. It's going to be about magnetic fields, so this will be closing up magnetic fields for us. We've had 3 weeks total of that. Next week is our exam. Our exam is on Thursday. So the PowerPoint we're getting through today, just like last test, the week before, the content shouldn't take us that long. I expect to hopefully be able to finish early on Thursday. If I do, we'll start the note card then. Either way, Tuesday will be our main review day. I will send out a survey just like before, asking, hey, what are the main things that you would like for me to cover? I will emphasize getting through the note card, and then whatever extra time I have, we'll do problem solving, clicker questions. There won't be any graded clicker questions. Like last time, the Tuesday, there will be no clicker questions the week of the exam. That's a pretty good rule of thumb. Any review days, there's no clicker questions. So, finishing up with Faraday's Law, next week is test. The 2 weeks after that, I think will be pretty interesting. It'll be all about light and optics. We'll say the word light, but really we're going to discover it's electromagnetic waves, electro for electric fields, magnetic for magnetic fields. Put those two words together and you make light. Electric fields and magnetic fields are light. So everything we've kind of covered can come together and we can talk about light. Pretty pleased with some of the slides. We'll actually get to talk about how the eye works, how corrective lenses work, all sorts of fun facts galore. And then how microwaves work, fun facts galore. So, otherwise, the other thing I want to point out is we have our withdrawal deadline this week. Our withdrawal deadline is this Friday. I'm sure you're all familiar with what withdrawal is. If not, it's basically your last chance to kind of get out of the class if things are going rough and your grade will not count, but you'll still owe the money. If you're on the fence, here's my suggestion to you as far as determining whether or not you should withdraw. Of course, we have test 1, but I also want you to consider all the quizzes since then. How have they been going? Have things improved? Or do they feel the same as they did before test 1? If they feel the same as before test 1, that's a red flag that things probably haven't changed, and it may be worth withdrawing, trying the class again. The great news is when you take the class again, you're not starting from zero. You've seen this stuff before. So yes, while it costs money, at the end of the day, it wasn't a lost cause. Your time was not wasted. You did hopefully learn something in here. If nothing, then I've done an absolutely awful job. But hopefully then the next time. So don't view withdrawal as a failure. View withdrawal as I need more time to study this stuff. Cut your losses, move on. It's completely okay thing to do in life, is to kind of take stock and retry again later. If at first you don't succeed, you don't give up. So, wanted to point that out because that is at the end of this week. Unfortunately, it's before the second test. So you won't know how you're going to do in the second test until after that. That's my recommendations. If you have personal recommendations you'd like from me on that, if you'd like me to weigh in, email me, office hours, come talk to me, etc. So, I'm going to finish up Faraday's Law this week. There you go. There's logistics there. Good news, or maybe for some of you bad news, I doubt it. There is not going to be a discussion section this week. Why? I never got the discussion questions to give you all. So that is outside of my control. They're supposed to give me those questions. They're 2 weeks late. So they have promised me that I will receive those by this Thursday, at which point next week. So as soon as I get those, I will have them posted within a day or two. So I will send an email out. I will send an announcement clarifying this. No discussion that you do not need to show up to discussion this week. I will still ask the TAs to be there in case you all want to basically view that as an office hours to meet with them, ask them questions, etc. But I'm not going to give you, there's no grade points for discussion this week because there is no problems that I can give you this week because I have not received them. Unfortunate, but outside of my control, so that's that. Last thing I'm going to point out to you all is at the end of class, so before the class I said I will not be here at the end of class to answer questions. Why is that? A while back, I told you all that at some point some people are going to come and try to get feedback from you all about how the class has been. Why? Because I want to do a better job of teaching. The only way you get better at doing anything is feedback. At the end of the day, I am serving you all, so you are the best feedback I can get. So in the last 15 minutes of class, they're just going to basically ask you all questions. How is Dr. James? How is your professor? Is he doing, like, what's good? What's bad? It's going to be kind of those same questions from the perception of instructor survey at the end, but, we'll get more detailed responses, and I would love it. So, really going to appreciate hearing from you all about that. And towards that end, I will leave the room, because you can't really give you maybe can, but it's far more comfortable to give feedback to someone when they're not sitting there right in front of you, staring you down the whole time. So, towards that end, I don't just want to leave the room. I want to be gone, so that way you don't feel like I'm hearing anything through the walls or anything like that. So, while I would like to wait out there to answer any questions you may have, to play completely safe, I will just be gone. I'll be off the campus, so you can guarantee I won't hear anything. Students online, I'm going to end the live stream because it would defeat the purpose of anonymity if I'm recording it. So unfortunately, online students, you won't be able to provide those, I say online students that are tuning into the recording. If you want to call yourself online students, that's fine. You won't be able to provide the feedback, though. Feel free to shoot me any emails with any feedback you have. There'll be the perception of instructor thing at the end, which always will exist as well. So there'll be an opportunity there. So there you go. So we'll finish. I will finish up here 15 minutes early, so whatever time that is, 4:35. Be great. All right. So with that in mind, last thing I'm going to tell you all. Something I'm going to do different for this. So I already told you all this test. 20 questions, 2 free response. You pick one. So a reduced version of the first test. So it's 20 instead of 25 multiple choice. It's 20. Instead of 3 free responses, pick 2. It's 2 free responses, pick 1. Okay, so it's a reduced amount. Hopefully that'll reduce. I'm confident with the time thing. I've made the test at this point. I'm going to go through it, time myself, see how that looks time-wise, evaluate. But I'm pretty confident this should fit nicely based on how I saw the timing last time. One thing I'm also going to include on this test, just to make things a little smoother, is I will have a formula sheet. I'm going to give you all the formulas that's going to be on it on the note card as well. This formula sheet will literally just be, hey, here's all the formulas. It's not going to say what they're used for. For example, it'll just be B equals mu naught I over 2 pi r. It will not say what to use that for. It will not say anything. That's what it'll say. I will send that formula sheet to you all in advance, so when you're making your note card, you can say, oh, okay, this is ready to be on there. I don't need to waste note card space for this. Okay? So that's another thing that'll be slightly different. Also, that way, if you are not here for the, say you lose your note card, say you forget it on the way to the test, whatever, you'll have something. You'll have something. That'll be, I won't provide my printed out ones like I did last time. The equation sheet will be your something. I will also put constants on there. I'll put the mass of an electron, mass of the proton, charge of an electron, charge of a proton, because I don't care if you all have that memorized. So stuff like that will be on there. Again, I'll send it out so you know exactly what will be given on the test, so you can save some room on the note card if you so desire. Okay? Now, any final questions before I get started? Cool. All right, let's get into electromagnetic induction. So, previous things that we need to remember. We need to remember what magnetic fields are. Hopefully you didn't forget those in the week and a half it's been. You need to remember what flux is. I'll remind you what it is, but we talked about electric flux. It's now going to be magnetic flux. It's going to be basically the exact same equation. You need to remember what area vectors are, again from flux. You need to remember how to find forces due to magnetic fields and what voltage is. So you'll see how it's all going to come together now. This is a very important section. Last time I showed you all that everything you've learned teaches you how electric motors work. I'll give you all the punchline by the end of this. You're going to learn the opposite of an electric motor. And I'll let you see if you, well, I'll just tell you what that is. If an electric motor takes electricity and makes movement, what if we want to do the opposite? What if we want to take movement and make electricity, i.e. generators, which are how we make electricity? You'll learn how that works by the end of these slides. Very, very important. So here are the learning objectives. What is magnetic flux? How to calculate it? What EMF is? That's the electromagnetic force. We'll get to that. How to calculate this EMF in a closed loop due to a changing field using Faraday's law. It's kind of the name of the section. Apply Lenz's law to determine which way that current will flow. And to identify a relationship between electric field and a changing magnetic field. There won't necessarily be an equation for that. Those are kind of a fun fact tacked on to the end. All right, already kind of told you all the punchline. Why do we care? Electricity is fairly important to us nowadays. And most people, if you ask them how is electricity made, they will say a battery or a generator. If you ask them how a generator works, they'll probably say you put gas in and it makes electricity. If you ask them past that, maybe they'll say something is spinning, and that's as far. That'd be my guess. Maybe people know more than that. You will definitely know more than that by the end of this. You'll know exactly how it works on a, at the end of the day, it's one of those exactly how it works. You can always keep asking why, and at some point it'll be that's the way it is. Why do things fall? Because of gravity. Why does gravity? Because of space-time. Why is space-time curved? Because that's how it is. Eventually you do have to be kind of satisfied, but you'll know more than 99% of people for sure. For good or for bad. Towards that end, before we have to start with flux, and this is going to see, do you remember how to calculate flux? Let's find out. If not, that's okay. I'm going to remind you. If you do, kudos to you. Great memory. How do you find electric flux? So I have an electric field pointed upwards with a magnitude of 8 newtons per coulomb. What is the flux through a plane, which is 2 meters by 3 meters? I will be so kind and even draw a beautiful picture for you all. There's my plane. That is 2 meters on this side, 3 meters on this side, and the electric field is pointed straight up. See if you all remember how to calculate flux. Will the answer be 0? Will it be 16 newtons times meter squared divided by coulomb? Will it be 48 newtons times meter squared divided by coulomb? Or will it be 1.33 newtons per coulomb meter squared? All right, we'll go to 150. We'll go to 2 minutes. We'll go to 2 minutes. Again, if you don't remember how to get this, that's okay. I will remind you how, because the equation for this is going to be almost identical to the one for magnetic flux, which is real nice. All right, and 3, 2, 1, 0. All right, so for those of us with awesome memories or just really organized notes, we remembered that the electric flux is the electric field times the area times cosine of the angle between the area vector and the electric field. How do you get the area vector? The area vector is the vector that's perpendicular to the surface, which is a real fancy way of saying take your pencil, put the eraser on the surface, there's your area vector. That's the easy trick that I always recommend to people. So in this case, if you put your pencil kind of on this plane, the area vector is straight up, therefore the angle is 0, cosine of 0 is 1. I purposely didn't make this too. So in this case, theta is 0, cosine of 0 is 1. So to solve for flux, it is just going to be the electric field, which is 8, times the area, which is 2 times 3, which will be 6. Plug all this in your calculator. Well, this is one of those. Yeah, use a calculator if you want. Use your head if you want. 6 times 8 is 48. There it is in all its beautiful glory. Let's see how we did. I didn't even look at the answers. But pretty decent. Again, great news. You all don't need to have these things memorized. Something I'm going to kind of mention as well is if you've looked at these slides in advance, you will see I've sprinkled review questions through here. And I'm going to continue to do that in like the next, anytime we're covering content, because the final is cumulative, I'll just kind of throw out some random questions here and there just to see if you all remember old concepts. Why? Because the final requires that you know some of these old concepts. So it'll help kind of keep it in your mind. So this was kind of a nice 2-for-1 special here. So getting to magnetic flux. What is magnetic flux? It is the same exact equation as that one, but instead of E, it's B. Ta-da! What is flux? It's how many arrows, how many of the magnetic field arrows pass through the surface. That's what flux is. It's kind of how much flows through it. These fields don't necessarily flow, but that's maybe a way you can think about it. How many of them pass through it? The more parallel they are, the more pass through it. If you turn that thing 90 degrees, none of it passed through it. That's why the flux will be 0 if they're perpendicular. The stronger the field, the more arrows. The bigger the area, the more arrows go through it. B is the magnetic field. A is the area of whatever this will be. In our case, it's going to be loops of wire. Theta is the angle between the magnetic field and area vector, and the units literally just come from the equation. What's the units for B? Tesla. What's the units for area? Meter squared. Ta-da, there's your units. They could be Weber as well, but I'm just going to keep it simple and keep it as any problem that I give you all, they'll be Tesla times meter squared. I don't need you all to know what a Weber is. That's not going to... Tesla times meter squared is good by me. I don't think I've ever seen the term Weber show up in anything ever, so that's why I'm not worried about it. Whereas newtons and amps and volts and those kind of things do show up all the time. So, but I figured I'd throw it in here just in case you're curious. And why do we need flux? You will see. It is very, very important. This magnetic flux is the reason I basically taught you electric flux in the first place, was just so that you'd seen it before we even got here. I mentioned that way back when I taught electric flux. I was like, why am I even teaching this? It's not, we don't use it for many problems. It's so that you were prepared for magnetic flux. Because magnetic flux is basically going to be this entire section. I mean, I can tell you right now, the punchline is the voltage that you generate is based on how much this flux changes. That's Faraday's law in a nutshell. You'll see that in a bit. So this whole section is find how flux changes, and that gives you the voltage that you'll generate. So we need to understand flux here because it is foundational to understanding how do you generate electricity with movement, which is very important to society. Very, very, very important. There is technically, I forgot, there is solar panels. Those don't make electricity this way. So batteries, solar panels, and generators are basically the 3 ways that all power is generated. All electricity is generated. It's those 3 mechanisms. Generators being the most common. All right. So great. Magnetic flux. Fantastic. Let's practice. All right. Y'all may not like this. This is going to, I'll draw a picture. We have an angle now. Why? Because it's good to be able to remind us, figure out what that angle is. So I'm going to draw the picture. Here's my loop, just like before. So if I have a magnetic field pointed upwards, that's the easiest one for me to draw. Bam. Pointed upwards with a magnitude of 8 Tesla. What is the magnetic flux through a closed loop, which is 2 meters by 3 meters, but now my loop is at a 30-degree angle with the XY axis. So this angle here is 30 degrees. And that's the magnetic field. What is the flux? we'll go to about 230 here. This one you got to kind of put some thought into and draw some arrows and all fun things. All right, in 5, 4, 3, 2, 1. So this problem basically boiled down to, is the area vector at a 30-degree angle or a 60-degree angle? If you got to that point, that was basically the hard part of this question. So I'll draw the area vector. It's 90 degrees to the surface. Basically take your pin, put it right there. And I'm going to show you all the quick way to think about these problems. No trigonometry, no triangle, like none of that stuff involved. Here's a trick to it. When it was flat, what was the angle between them? It was 0. Think if I tilt it 10 degrees. Did my angle change that much? If I just slightly lift it up 10 degrees, my area vector will only move a small amount. You can think of this surface. I don't have anything wonderful. Oh, I do. There's a convenient piece of rug here for some weird reason. Yeah, I don't know why, but it's great. If I tilt this thing slightly, my area vector didn't actually change that much. So, if I tilted it 30 degrees, my area vector will just move 30 degrees. It'll move a little bit. If I move this thing a lot, think of the extreme case. If I turn it 90 degrees, what's the angle between my area vector and that magnetic field? Now my area vector is this way. Think of the extreme situation. So sometimes you can figure out these things by just kind of thinking through what happens to the angle. What happens to this area vector? Does it move that much if I lift it up? So this is 30 degrees. The longer way involves recognizing that we kind of have to draw some triangles. Again, this is that classic. We love these so much, right? We have to draw a bunch of angles, and we have to draw, that one's 30 degrees. So based on these, we're able to figure out that this is going to be 60 degrees. How do we figure that out? Here's the key to that. If you ever, let me erase a bunch of things here. If we have a straight line passing through something, we know that this angle is going to be the same as this angle, and therefore we're going to know. Let me think through how to, I'm going to come back to this one to draw the better way of doing it, because off the top of my head, if I just try to fudge through this, it's not going to be beautiful. Honestly, the way I solved these is the first way I did. I don't try to draw a bunch of triangles. But the math should work out. So I'm going to come back to this one after I spent some time thinking about it, because I don't want to just try to flub my way through this and then wave my hands and say that that's right. So by the end of class, I'll come back to this and prove to you all why this is 30 degrees. But I'm not going to waste the time on flubbing my way through it. The easy with the triangles, but I will come and fix that for you all. So it'll kind of be stewing in the back of my mind. For now, know that your answer is this. Let me write out the math. Magnetic field, a B turns into that. B, A cosine theta, using our kind of logical idea that lifting it up a little bit means that's going to shift a little bit. We put in our numbers, 8 times 2 times 3 times cosine of 30. If you plug that into your calculator, you get 41.57. Cosine of 30 is square root 3 over 2, so it's not a nice number, hence why our final answer is not a nice number. 41.87, and we're good physicists in this room, so we put our units after because that's very important. So, anyway, again, I'll come back, draw some beautiful triangles later. For now, though, let's not get hung up on that. All right. Told you all there'd be random review questions thrown in. What is the current on path 1, 2 in the circuit below? Why is this randomly thrown in? Because this will actually show up on the test. It's good to see if you kind of can do it off the cuff. These are the kind of problems, just good random review problems. So I've got here a 9-volt battery with a 10 kilo ohm resistor for R1, a 2 kilo ohm resistor for R2, and a 1 kilo ohm resistor for R3. find the current in path R, path 1, 2. What is the current here? There's a couple steps involved here, so I'll give you all some time on this. But again, this whole week's Faraday's law stuff won't take us long to get through, so I just kind of want to throw in some random test review kind of things in now. This will help see if you all are on pace and ready. If not, you got time to study. Again, this is going to take you all a little while, so I'm happy to spend. We'll probably go to like 3 minutes or so on this. All right, it's about, we'll maybe go an extra 10 seconds or so if you need to. Obviously, that's okay if you are taking time. This one, it's technically a 2-step-ish problem. Neither step is very big, but you do have to know that there's 2 steps involved. All right, we'll go to 3:30 and call it safe again. A few more seconds is fine. If you're not sure, that's all right. I will show you how. But this is a great problem because it tests so many different things. In 3, 2, 1, bam. All right, so before we begin this problem, you kind of have to think, how am I going to solve this? How am I going to find the current through this branch? And remember, y'all, basically, whenever you do these problems, the first step that should come to your mind is to take this and turn it into a single resistor. That should be your first kind of thought when you see these complicated circuits. Why? Because if I draw that green path over here again, the one that we're trying to find the current through, we will see that I find the current, and that current will be in series with that net resistor. And if we remember, series current is constant. The current that is in this green part is the same everywhere through this circuit here. So long story short, if we can find this net resistance, we know that this is going to have the voltage of the battery, and we can use our beautiful equation V equals IR to find the current, which will give you the current through that green path as well. So how do you add resistors in parallel? Another great skill that we'll need to know, and it'll be on our formula sheet. R net is 1 over R1 plus 1 over R2 plus 1 over R3. This is how you add resistors in parallel. It's the ugly one. Capacitors in series is the ugly one. Resistors in parallel is the ugly one. I mean, beauty is in the eye of the beholder. Maybe I should use the word complex to be a bit kinder to this equation. Though, does it have feelings? You decide. So 1 over 10 e to the 3 plus 1 over 2 e to the 3 plus 1 over 1 e to the 3 equals 0.625 e to the 3, or 6.25 e to the 2. Why did I write it that way? Because I will tell you all how I plugged this in my calculator. I plugged in 1 over 10 plus 1 over 2 plus 1 over 1, and then at the end I just chopped on the times 10 to the 3. It's a nice handy thing you can end up doing. So, 0.625 e to the 3. And remember your rule for parallel. This is another helpful reminder. In parallel, my net resistance should be smaller than my smallest resistor. My net resistance should be smaller than my smallest resistor. 0.625 is smaller than 1. There you go. 1 was the smallest, it's smaller than that. That's just a good rule to keep in your head. All right, great. We got the resistance. I'll write it a bit more normally. 6.25 e to the 2. Same number, just written 2 different ways. How do I get current? V equals IR. I equals V over R. I equals 9 over 6.25 e to the 2 equals 1.4 e to the minus 2 amps. And I'll fix these to capital E's. I used to use lowercase and realized that may be confusing. Exponential. A lot of good skill sets here, y'all. If you don't remember any of this, that's okay. You got a week and a half or so to kind of jog your mind on these things. But this is one of the first things that will show up. Very nice, y'all. That did get it right. That is a good sign. If you didn't, that's okay. You got a week and a half to kind of refresh your mind. I know it's been a hot minute. That's part of the reason I'm doing these reviews, is I know after a week of spring break, your mind has been filled with other things, hopefully good things, and that maybe pushed out some of the physics. All right, so back to the stuff we're learning today. Faraday's law. Faraday's law, this is what the entire rest of the slideshow will be about. That and Lenz's law, which is no math required. This is literally the only equation on the entire slideshow. At some point, I think I put an N in front of it, and that's the only difference I make. Faraday's law says, it's kind of a fun history lesson. So like all scientific discoveries, someone discovered them. Whoever discovered them often gets it named after. Faraday discovered it in 1831. Joseph Henry had no idea what Faraday was doing. As these things happened, 2 independent people were both studying the same thing. Faraday published first, and in academia we call this getting scooped. It's when someone is working on the same thing as you, and they publish their findings before you finish yours, and they get all the credit, and then you say, yeah, they're right. And that's your credit. You've confirmed their results, but they get pretty much all the credit because they did it first. Ain't that how things go? Just a fun fact. It's a fun phrase. So what did they discover? They discovered that this EMF, we're going to call it the electromagnetic force, it's going to turn out its voltage. But we use a different name for a reason. As we talk about this, we'll learn why. The voltage, I'm just going to use that word now because we're more familiar with it, induced is the negative change in the magnetic flux per unit of time. Long story short, find how the flux changes with time. That's the voltage in the wire. And if you have voltage, you have current. And if you have current, you can do all sorts of cool things like turn on light bulbs. So this equation, to put it in maybe more layman's, like simpler terms, find the rate of change of the flux with time. That's your voltage. The units, as I said, are the volts. This is epsilon, lowercase epsilon in the Greek alphabet. It is used for electromagnetic force because it looks like an E. That's the best reason I can think of for why it is that. And the equation here is literally just the equation for flux I gave you all, divided by time. That's it. Why is it called electromagnetic force and not volts? Because it's kind of helpful to think of it almost like a force that's moving these charges in the wire. You can technically measure it, and you'll measure volts, but at the same time, in certain situations, it's hard to measure. If we have a single loop, I can kind of talk about that. If you're very interested why that's kind of weird, I was talking to one of my coworkers about it. But if you can measure this, and it's just volts. It moves the charge. You change the flux and magically a current starts appearing. What makes this current? This EMF. That's why we kind of invent this term EMF, and we call it, and it has 8 volts. So looking at this equation, what are the 3 things that can change to generate this EMF? What are the 3 things we can change? Time's going to be a given. Time's going to change. So that's not going to be one of them. What are the 3 variables that can change to generate voltage? What are the 3 things we can modify? Sure, what's one? That's one. You can change B. So I'll rewrite the equation over here. So EMF equals the change in flux over change in time. It's a negative. We're going to see why it's a negative. I'm going to go ahead and tell you all, you're not going to have to worry about the answers being negative on any of the problems, but this negative has a meaning to it. We'll get there. For now, just recognize that negative means something, so we do have to kind of put it here. B, all right, so great. We got B. You can change B. What's the other thing you can change? You can change the area, and what's the last thing you can change? The angle. Look at that. It's literally the 3 things that make up the equation. Those are the 3 things you can change. Make the field stronger or weaker, make the area bigger or smaller, or change the angle. I will let you all think about which one is the easiest to change, and by the end of the slides, I'll kind of reveal which one it is. So for now, looking at these 3, when you think about a generator, we are changing one of these 3. I'll let you all think about what it is, and when we get to the end of the slides, I'll tell you what the answer is. What does a generator change? Is it changing the magnetic field? Is it changing the area? Or is it changing the angle? Kind of just have that ruminating a bit somewhere. So, let's just literally jump right into a problem where I'm going to solve one out. This is a fairly straightforward problem about flux, where one of the variables is changing, and we're going to identify which one. So I'll show you all how to do it, then I'll give you a quicker question, kind of test you on it. What is the induced EMF in a circular loop of wire with radius 2 meters if its area vector is parallel to a magnetic field which changes from 4 microtesla to 2 microtesla in 5 milliseconds? Here's my loop. There's my area vector. There's my magnetic field. It says they're parallel, so they're parallel. They're lined up with each other. We'll draw a better loop. There it is in all its beautiful glory. Again, how do you find the direction of the area? In this problem, it says it's parallel. My picture just reflects that. They're lined up with each other. We write down our givens. What is given? We have the radius of this loop. The radius is 2 meters. We have 2 magnetic fields here. It says it changes from 4 to 2. So we have a final magnetic field, 2 microtesla. We have an initial magnetic field that is 4 microtesla, and I'm actually going to attempt to write this there. Well, that one's not getting erased, so it's just going to look ugly. 4 e to the minus 6 Tesla, and we have our time, and we have to be very careful to put it in seconds. Okay, so that's all our givens. We are solving for the EMF. And I just gave you all the equation for the EMF. EMF is the negative change in the magnetic flux. You know what? I'm not going to even put I say I'm not going to put it. My thing is decided it's not going to erase, so whatever I write down is final. Change in BA, to the power of Control Z, I can erase everything. Wow, that's terrible. Erasers are a beautiful invention, which my computer has decided to ignore. So let me go ahead and save this, close this, reopen it. That usually fixes the problem. But while I'm doing so, try to finish the problem. Y'all don't need me, right? Try it out. I kind of pointed you all in the right direction. You got a handful of seconds. Y'all can see what I taught my physical sciences kids yesterday was about chemical bonding. Bet you wish you were learning this lesson. Nah, too easy for y'all. All right, back up we go. Is it fixed? Absolutely not. Keep working on it. Close all the PowerPoints. If not, we're just going to go to a new slide and I'll try to write it from scratch. This is one of the things I promised you all at the beginning of this class. Technology is one of the things outside of my control. All right, so just going to quickly rewrite everything I just wrote because clearly it's not here anymore. The initial equals 4. But my eraser works, so ain't that a hoot. 5 e to the minus 3 seconds. 2, we're solving for the EMF. 3, EMF equals negative, change in flux. If you all were a calculus class, I would use D's instead of these triangles. So if you ever see me do that, that's why. Going back to my roots. Negative change in B, a cosine theta over change in time. All right, great. Caught back up. So when we look at this change, we just said 3 things can change. And so when you look at these problems, you have to decide what is changing. Is it the magnetic field? Is it the area? Or is it the angle? And this problem, especially with step 1 kind of written down, hopefully it's fairly straightforward. Which one's changing? Which one is it? With confidence. Oh, come on. Which one has a final and initial? B, there we go. Yeah, it's B. B is the one. If you have a final and initial, that's the one that's changing. You all got to believe in yourselves. All right, so I'll copy this stuff on over because I have run out of room as always. The nature of trying to fit everything on a PowerPoint slide. As I've mentioned before, when you all do physics problems, give yourself a healthy amount of space. Something I'm also going to do on the test is that formula sheet will be kind of your scratch paper. So instead of me having to run around and give everyone scratch paper, it'll be built into the test. All right, step 4. You all wisely informed me that the area is not changing, the angle is not changing, but the magnetic field is. Over change in time, we recognize that if they're parallel, the angle between these is going to be 0. Therefore, cosine of 0 is 1. That's going to become a trend in most of these problems. So negative, what is the area? It's going to be pi r squared. We're really good at circles in this class. Times BF minus BI divided by the time, which is just the time. Change in time is just time. That's also going to be a thing in basically every problem. Anytime I give you all time, that's a change in time. I'm never going to say from 1 to 3 seconds. No, that's not going to happen. All right, so negative pi times 2 squared. Now it's just plugging in numbers. Times 2 e to the minus 6 minus 4 e to the minus 6 all over a beautiful straight line. 5 e to the minus 3. These problems, in my opinion, are fairly straightforward. Whatever is changing, subtract those 2 things, divide it by the time, and make sure you have everything else. So make sure you have the area there. If the angle was anything that wasn't, basically all your problems will be, the angle is going to be 0 unless the angle is the one changing. I can basically promise you all that now. I'm not going to give you a problem like this where the angle is like 30 degrees or 60 degrees or anything like that. But there may be some problems where the angle changes, and by May, there will be, guaranteed. One of the problems I'm going to solve with you all will be in a changing angle problem because it's kind of the funkiest one. Changing area, straightforward. Changing magnetic field, straightforward. Changing area, not too bad as well, but it's the most tricky of the 3. But it's the same exact principle. All right, so we get a negative, which cancels out our other negative. And we get 0.005 volts. Wow. What a What a hefty voltage that is. This problem has a lot of useful qualities to it in terms of the final answer. One, these are realistic magnetic fields. I told you all this before. 1 Tesla is huge. So like the MRIs you all go in, magnetic resonance imaging, I wish I had talked about those more, but didn't quite get to it. They make very strong magnetic fields. 3 to 4 Tesla. Doesn't sound big, but put a metal chair near it and you will see how strong that is. There's great videos online of that. So this is a more realistic magnetic field. This is a more realistic one, micro Tesla, maybe millitesla. And this is a quick time. This is in 5 milliseconds, which is pretty quick, which means we would expect maybe a bigger answer, but this just goes to show it is not easy to make this voltage. 0.005, you either need a huge changing magnetic field, or maybe there's some other ways to make a big field. Maybe there's some tricks we could do. Here we only have 1 loop. What if we had more loops? That's kind of one of the key ways of doing it, and we'll get to that. So, y'all try it for yourself. A circular loop of wire has its radius shrink from 3 meters to 1.5 meters over 5 seconds. The area vector of the wire stays parallel, started parallel, stays parallel, with a magnetic field of a magnitude of 4 microtesla. What is the induced EMF in this problem? This one will take you a little bit. It's not one you can do in your head. I can't do it in my head. Let's put it that way. You know, students always surprise me. There's many things you all are better at than I am, that's for sure. Thank goodness for it. It means I don't have to be a doctor. In the same process, what's given, what is changing here, calculate that change. And then plug everything in and solve. For this problem, we'll probably go to like 3:30 again, because again, it is involved. It involves a calculator, specifically. All right, about 30 more seconds. We'll go a little bit longer. I feel like I'm missing enough people. We'll go to 3:40. Give you all a whole 10 extra seconds. In 5, 4, 3, 2, 1. So this problem is the most ridiculous one. How do you even make a loop change its radius from that to that? I mean, you could maybe think of some creative ways. This is the least likely to happen, but it's still useful for us as far as applying the equation and kind of working through it. But I'll straight up tell you, in the real world, no one's doing this. So let's go ahead. What's our givens? Our initial radius is 3 meters. Our final radius is 1.5 meters. Our time is 5 seconds. And our magnetic field is 4 microtesla. 4 e to the minus 6 Tesla. We're solving for the EMF. Our equation for EMF is the negative change in flux. And actually, I'm just going to change in B A cosine theta over time. And same thing, what's changing in this problem? I already kind of said it, it's the area. Now, this one's kind of a little trickier than the last one to solve mathematically. Conceptually, same process. The magnetic field, it doesn't say it's changing, so it's not. The angle, it says it stays parallel. That's not changing. So the area, fun thing, y'all, only one of these will change. I will never give you a problem where 2 of these variables is changing at the same time. Why? Because that would involve calculus. And we don't know calculus. Well, we don't have to know calculus. Let's put it nicer that way. Some of you may know calculus, but you don't have to. So you don't have to bother with it. So the magnetic field pops on out. The angle is going to stay, as I told you, it's going to be 90 degrees. They seem to all be that way. How kind of me. So the magnetic field pops out. The area, pi r final squared minus pi r initial squared. And you may already be able to see at this point if you made a mistake on this problem, which some of us did, it's because you forgot to square those radiuses. If you made a mistake here, you may have forgotten to square those radiuses, and that's where the problem came in. So now I copy all this over to another slide, because as always, space is a premium. So I copy all this over, I chuck it over here, and I plug in some numbers. All right, so negative, the magnetic field is 4 e to the minus 6. Pi is pi. I'll leave it in there. You could pull out that pi. They both have it. If you want to pull it out and not have to multiply by it twice, great. If you want to leave it in there, great. Gets you there either way. 1.5 squared minus pi times 3 squared all over 5, and you get a final answer of 1.70 times 10 to the minus 5 volts. So it looks like your answers are split. Very likely you forgot the squared. That's probably the reason why. Technically it was 1.699, but you rounds to 1.7. Remember, when I give you all any of these questions, I will never give you any answers that are so close together that a rounding mistake would throw you off. In this case, these two numbers are an order of magnitude 10 times bigger than each other. So, there you go. If that doesn't, yeah, yes, sir.
For the top portion of pi r f squared.
Yes.
So, if you do like the difference in radius and multiply that number by pi.
Yep. No, it's the same thing. Pi here, they both have pi, so I can pull that pi to the front, which is what I honestly did in the calculator. Okay. I didn't do it here because I felt like this is just maybe a bit more straightforward. See, but that is honestly the easier way. Pull the pi out so you don't have to plug it in twice. Yep. Great question. All right. I'm going to give you all, so here's kind of the last equation. It's the same one with an n in front of it. There you go. If one wire has a surface area of A, then 2 have a surface area of 2A, 3 have a surface area of 3A, 4, 5, 6, 7, 8. We don't just work with one loop. If you'll have ever seen a generator and you've ever looked inside it, it is coils on coils on coils of wire. The more you can jam in there, the better. Because each one is going to multiply your voltage. If I have 500 coils, that is 500 times. Take any of the problems we just did, and if I, instead of one coil I had 500, it'd be 500 times the voltage, which is real nice if we're wanting to generate thousands of voltages to shoot out across miles of wire to get to people's houses. So, this is the more general form of the equation. Exact same thing. EMF is the change in flux over time. Put an N in front of it for how many loops you have. Because the real world, they don't use one loop. They use hundreds, thousands. If you want a field to be 1,000 times stronger, if you want 1,000 times the voltage, put 1,000 loops instead of one. Real simple. You need the insulation around the wire, because say I have a wire, a loop like this, and I just put another loop on top of it, but I don't have insulation. I have literally just made a fat wire, because the metal's touching and it's just going to go around that. If you want these loops to work, you need to have a loop, and you need to have some separation between them. So that way the electricity is actually going in those loops and not just chunking together. How to kind of visualize that. Here's a loop. I need this loop that I put on top to be separate. I don't want the metal touching. You can think of the metal touching, it literally just looks like a fat wire. I don't want a fat wire. I want 100 loops. 100 independent loops from me. I mean, they kind of connect together to make a coil. But that's really important. Good news, none of you have to make these, so don't worry about it too much. The tighter they are, the better. So they experience that same change in magnetic field. Magnetic field varies drastically with distance. It drops off, 1/r. So you want them to get that maximum change in magnetic field. You want it to be consistent, just so it's easier to kind of calculate. So, I've got about 8 minutes till the foretold time. Good news, I basically taught you the main things. Thursday will be quick. What I need to teach you all there is the direction that the current will flow based on this changing flux. So, ironically, today was all the numerical calculations, and Thursday will be more conceptual. Flipped from our usual script. Real quick, I promised you all I would show you where that 30 degrees came from, and it's been ruminating in the back of my mind. So I'll real quick show you all that. If I draw this here, here's where that 30 degrees comes from. This is 30 degrees. So again, I recommend doing it logically. Just think, if the angle increases a bit, that tilts a bit. If you kind of just think through what would happen on the extreme cases, that's easier than having to do a bunch of trig. If this is 30 degrees, this is 30 degrees as well. Why? Because if you have two lines and a thing that goes between them, these two angles are the same. So that's step one. That's 30 degrees. Okay? If that's 30 degrees, this is a 90-degree angle. So if that's 30, that means this is 60. And you're like, all right, great. Guess what I get to do now? Make another 90-degree angle. And if this one is 60, these together are 90 degrees, that's 30. You can see how much more work this is than just thinking of the extreme cases. What if I tilted my thing 90 degrees? Oh, great, now the angles are 90 degrees together. What happens if I tilt it a little bit? The area vector tilts a little bit. Honestly, that's what I do for most of these. I try to avoid the trigonometry as much as possible because, as you can see, it's a bore. Whatever. Again, good news. I'm not going to ask you one like this. So if you're really stressed about it, you don't need to be. Yeah?
I think this is really straightforward if you just follow the equation, right?
You just have to know if it's cosine of 30 or cosine of 60. And that's the hard part. Sometimes it's 30, sometimes it's 60. You have to think through the logic about what's what. What angle goes with what angle.
What do you mean by you won't ask us one?
I won't ask you one where it's like 30 degrees. I won't literally like a problem like this where it's at an angle and you have to kind of guess what it is. I'll make it more obvious and say it's a 60-degree angle between the area vector and the magnetic field. Yeah?
What case would it be different? Wouldn't the angle you're getting just like...
If I said maybe somehow worded it to be this angle, which would be 60 degrees. There's a way I say it's a 60-degree angle with respect to the y-axis. Something like that. Like there's ways I can word it. Don't bother. At the end of the day, I want you all to know how to use this equation. I'm not as worried about all this trig angle stuff. All right. Do you all want to start now? Do you want me to? All right, great. So at this point, I'm going to go ahead and make my adieus. Next class, I will solve another problem. We'll talk about the rotating case, and we'll get to Lenz's law. It looks like I have a bunch of problems here. Wow, look how many. It's not as bad as it looks. Okay, I lied. There was one more problem here to kind of do, but we'll get through this quick. It's not that much more we need to cover conceptually. It'll be fairly straightforward. The math will be fairly straightforward. This one will definitely be your least favorite, because it's going to combine everything together. But least favorite doesn't mean you can't do it. Least favorite just means we spend a bit more time on this versus the rest. It'll all work out, don't worry. We will have the time, I promise. We went a little slower today for a few reasons. So with that in mind, I will save this so that it doesn't corrupt and ruin everything. I will leave the premise, completely leave UCF entirely.